Hello and welcome to this lecture on fundamental of electric drives. In the last lecture, we were discussing about the characteristic of DC motor, especially shunt motor and series motor. Now, today we will be discussing about the speed control of separately excited DC motor fed from control rectifier. So, let us see how the speed can be controlled by using control rectifiers. Now, let us see that how many types of control rectifier we have. We have especially two types of control rectifier. One is called a full control rectifier, other is called a half control rectifier. So, let us see the topology of these two kinds of rectifiers. This is a thyristor bridge. So, we have the SCRs here and this is feeding the armature of a DC motor. The field is separately excited, this is the field winding, and we have the AC supply which is the input to the bridge. Now, the current here is I A, the output current, and the output voltage across this is V A. Now, if we see that in this case the current can only flow in one direction, because this is a control rectifier, SCRs can only deliver current in one direction. It means the current here can only come from the SCR to like this, there cannot be any reverse current flow. However, the voltage V A can be positive, it can be negative, because the input here is an AC supply, this is V S. So, V S can be expressed as V m sin omega t. So, if we plot this input voltage, it will be an alternating voltage like this, V s, x axis is omega t axis, this is pi and this is 2 pi. So, the input is a alternating supply, the output in this case is, we will see that this is the average will be DC. However, the average can be positive or it can be negative, because it is a full control rectifier. So, this is called a full controlled rectifier. And since the input is single phase, we can call this to be a single phase full controlled rectifier. Now, if we plot the average voltage and average current in a xy plane, we will take the voltage in the y axis and the current in the x axis here. This converter can operate in the first quadrant and the fourth quadrant. So, this is a 2 quadrant converter which can operate in the first quadrant and the fourth quadrant. The voltage can be positive or negative, current can only be positive. Now, let us see another type of control rectifier. Here also we have 4 devices. However, 2 of the devices are SCRs and 2 are diodes. This feed the armature of a separately excited DC motor. The field is separately excited. The current here is IA, average current. The average voltage here is VA. The input is again an AC supply. So, here this is called a half controlled rectifier, and since we are talking about single phase, this is called a single phase half controlled rectifier. Now, what are the operating quadrants here? The output voltage, because we have these 2 diodes here, this diode will be giving a freewheeling path. So, whenever the voltage will try to be negative, these 2 diodes will be forward biased. So, there is a freewheeling path here which is existing. So, the voltage VA can never become negative. So, this is why this is called a half control converter, and this operates only in first quadrant. So, let us see the operating quadrant here. So, if we plot the operation of this converter in VI plane, VA is in the y axis and IA is in the x axis. So, the operation only happens in the first quadrant, because in this case the voltage can never be negative, current of course cannot be negative because we have SCRs and we have diodes. Similarly, this is for single phase converters. Now, single phase converters are used for lower power applications, especially when the power is less than 10 kilowatt typically. These are used for those applications, low power applications. When the power is higher, maybe more than 10 kilowatt or more, we go for 3 phase converters. So, in case of a 3 phase converter, we can also have a similar topologies. We have the 3 phase converters, and this is the bridge we are talking about, bridge converter, and these are all SCRs, and this we are feeding the armature of a DC machine. The field is separately excited and the input here is 3 phase. So, 3 phase AC input and the output current here is IA and output voltage here, average voltage is VA, we are plotting the average voltage. Now, if we see this bridge, the input is a 3 phase balanced voltage supply and output voltage can be positive, can also be negative, the average voltage. So, as we have seen in a single phase case, in 3 phase also this can operate in first quadrant and the fourth quadrant. So, if we see the operating quadrants here, this is the voltage in the y axis and current in the x axis. So, we see the operating quadrants. So, this is also a 2 quadrant converter. This can operate in the first quadrant as well as the fourth quadrant. So, we call this to be a 3-phase full controlled converter, and this usually this is a bridge converter. This is in the form of a bridge. So, we call this to be a bridge converter. Now, similarly we can also have half controlled converter, 3-phase converter. So, what we have here is we have 6 devices as before. So, we have in this case 6 devices, 3 of these devices are SCR, 3 are diode. So, half of the devices are controlled rectifier and half of the devices are uncontrolled rectifier. Diode is an uncontrolled rectifier. The input supply here is again 3-phase. So, 3-phase AC supply, and the output here feeds the armature of a DC motor. The field is separately excited. We have this current here IA, and the armature voltage here is VA. Now, if we see the operation of this converter, this converter also operates in one quadrant only. We have the XY plane where we have plotted the voltage and current, but this converter can only operate in one quadrant, and that is why this is called a half controlled converter. The voltage here cannot be negative, because there is a freewheeling path which is existing here through one diode and one SCR. So, whenever the voltage is negative, the freewheeling start between the diode and the SCR, there is a path of freewheeling which will bring the voltage down to 0. So, the voltage VA, the minimum value can be 0, and this can only be positive, this cannot be negative. So, this operates only in first quadrant. So, this is quadrant 1. So, this is called a 3-phase half controlled converter, and see this is a bridge. We can sometimes call this to be a 3-phase half controlled bridge converter. Now, let us see how we can analyze the operation of a separately excited DC motor when fed from a single phase full control converter. So, we are feeding from a single phase full control converter, and this is separately excited DC motor. Now, let us first draw the circuit diagram here. So, we have a single phase bridge here, we have 4 SCRs, and what we do here, we replace the motor by its equivalent circuit. So, this is the armature of the motor. The armature consists of a resistance, an inductance, and a back EMF. So, this is the representation of the motor. So, we call this armature of DC motor. So, the input is fed from an AC source, so this AC source is having the magnitude or the value of the voltage is Vs. Now, Vs is the instantaneous value, and this Vs is expressed in terms of its various voltages. So, we can say that Vs is Vm sin omega t. So, this is a single phase full controlled bridge. Now, we can control the output voltage by controlling the triggering angle of the SCRs. So, SCRs can be triggered at certain angle alpha, and the current here is IA, and the voltage which is here is VA, the armature voltage VA. Now, when we write these small letters, we mean the instantaneous values, the current which is instantaneous, the voltage also which is instantaneous. Now, this particular converter can operate in two different modes. One is called a continuous current operation, other is called a discontinuous current operation. Now, we will try to see this two in different parts of the lecture. Now, let us first see discontinuous current operation. So, we call this to be discontinuous armature current. When the armature current is discontinuous. So, what happens? IA comes down to 0. So, in this case, suppose we want to plot the output voltage. We have the input which is the sine wave, so this is 0, 2 pi, this is pi, and then this is 2 pi, 3 pi and so on, and we have a back EMF. This is the motor back EMF. And we triggered this SCR at an angle which is alpha, and this happens in every half cycle. So, this is the rectified waveform. So, here also we trigger it at an angle alpha. So, this value is pi plus alpha. So, the current rise from 0. When we trigger the SCR, the current starts from 0. Now, we see that we have an RLE circuit. So, when we trigger the SCR, let us say we have T1, T2, this T1 and T2 are triggered in the positive half cycle, because they are forward biased in the positive half cycle, and T3 and T4 are triggered in the negative half cycle. So, at this instant we trigger T1 and T2. So, they are forward biased, they will go into conduction. So, when they go into conduction, we will have a current. The current will start from 0 and will somehow come down to 0 before the triggering of the next pair of SCRs. At pi plus alpha, at this instant, we trigger the next pair of SCRs. The next pair of SCR which are triggered in the negative half cycle are T3 and T4. So, we have T3 and T4 are triggered in the negative half cycle. So, the current will again start from 0 and will die down to 0 before the commencement or before the triggering of the next pair of SCR, which is again T1 and T2, because the operation is periodic. So, this is the nature of the current. So, we have IA varies like this. So, this is our current which we are seeing here, this is IA. Okay. So, the current starts from 0 and goes down to 0 again, and this angle at which the current again goes down to 0 is called the extinction angle. This angle is called beta. What about the output voltage? Output voltage will be rectified voltage, no doubt, but this will have a typical waveform. Now, when we trigger the SCRs, the output voltage will be same as the input voltage, okay? Because when we trigger, let us say, these two SCRs, these SCRs will go on conducting, and so the input is connected to the output. So, this is the path of the current, and it will be basically returned back like this, back to the source. So, when we trigger T1 and T2, the output VA will become Vs, Vs is the source voltage. So, this is the output here. Okay. At omega t equal to pi, it still continues, because the current continues to flow beyond omega t equal to pi. So, we have continuity of current, and the current only comes down to 0 at beta. So, the current flows till beta. So, output VA is same as the input, that is Vs. Now, at beta the current comes down to 0. So, when the current comes down to 0, this current is 0 now, circuit is disconnected. So, this part of the circuit is disconnected, the source is disconnected from the load. So, the output voltage will be same as the back EMF. So, in this case the voltage here is same as the back EMF. So, it will be like this, and then at pi plus alpha, T3 and T4 are triggered. Again the current will be diverted from this branch. We have the current which will now flow through T3 and T4. This two will be taking the current. So, T3 and T4 will be taking the current. So, the voltage across the load will reverse. So, this is the voltage which will be appearing across the load. So, this phenomenon is periodic. So, the output voltage will look like this. So, even here also the output voltage will have the similar pattern, because we have a periodic waveform. So, the output will be of this sort. So, this is the output voltage VA. So, we have here two distinct intervals. One is called the powering interval, other is called the zero current interval or coasting interval. So, let us see that we have two intervals. When omega t is greater than alpha, is less than beta, from this part to this part, the output voltage is same as the input voltage. So, this is called the powering interval. This is called the powering interval. And in this case, what happens here, that the output voltage is same as the input voltage. And we have another interval in which omega t is greater than beta, but is less than pi plus alpha. This is the small interval which during which the output voltage is same as the back EMF. So, this interval is called the zero current interval. Or this is also sometimes called as coasting interval. Now, during the coasting interval, the output voltage is equal to the back EMF. Now, we have two different modes here. One is called the powering interval, other is called the coasting interval. We will try to analyze these two interval separately. Now, let us take the first the powering interval. In powering interval, what happens is the following. This interval is omega t greater than alpha, less than beta. Now, in this case what is the input? Input is same as output. Output is in fact equal to the input voltage Vs. So, what is this voltage here Va? Now, if we see this armature voltage Va, armature voltage consists of 3 different voltages. One is the drop across the resistance, other is the drop across the inductance, and the third drop is the back EMF. So, we can say here that Va is equal to the resistance drop RAIA plus the inductance drop LA DIA by dt plus the back EMF which is E. Now, this is the equation for the powering interval. Now, the input is a sinusoidal supply, the input Vs is a sine wave. So, we can rewrite this equation by substituting for input voltage Vm sin omega t is equal to Ra Ia plus La dia by dt plus E. Now, this is a first order linear differential equation and we assume that the back EMF is constant. So, we have to find out the solution of this differential equation. Now, this differential equation, if we solve this differential equation, this differential equation will have 2 parts. Now, Ia will have a steady state component in the steady state plus Ia will also have a transient component. Now, what is the steady state component? The steady state component is a component when t tends to infinity. So, it means in the steady state the inductive voltage will be the inductive reactance into the current. So, in the steady state we have an RLE circuit. Now, if you apply the steady state component here, this is Vm by Z sin omega t minus theta minus E by Ra. So, this part is the steady state part and we have a transient part, that is A exponential, since we have an RL circuit we have an exponential part which is t by tau. Now, this part is the steady state part. And this part is the transient part. Because at t tends to infinity, this part will be equal to 0. Now, the steady state part has got 2 voltages. One is Vm, the applied voltage, that is Vm sin omega t, and we have a theta here. Theta is called the power factor angle, which is equal to tan inverse of omega L by R is called the power factor angle or impedance angle. And we have another voltage, that is E, that is the DC voltage. The DC voltage will only see the resistance in the steady state. So, we have this E here and E is opposing the flow of current. If you see, Vs is helping the flow of current and E is opposing the flow of current here. So, E will have minus E by Ra, and then we have a transient component which is A e to the power minus t by tau, and tau here is the time constant, which is this is La by Ra, omega La by Ra, and time constant which is La by Ra. We can call this to be the armature time constant, which is tau A. So, this is the solution of this equation. We have a steady state component and we have a transient component, and the transient component will die down to 0 as t tending to infinity. So, we stop here for today's lecture. We will try to find out this constant A in the next lecture.